once asked me, how I proved the Poincare conjecture. I said, well, it's just a homeomorphism. I just had to say where every point went. And I did. Vitalik Buterin. They claimed that this formula could be derived from Kant's categorical imperative. And I didn't know who Whitney was. Here was this guy who manifestly from his first draft, which we had, did not know much topology, but he had completely cleaned the clocks of the topologists by having this tool of quantum field theory under his control.
Welcome, everyone, to the Cartesian Cafe. I am your host, Tim Nguyen. Today, we're very lucky to have Michael Freedman here with us. Mike is a mathematician who was awarded the Fields Medal in 1986 for his solution of the four-dimensional Poincare conjecture. He has also received numerous other awards for his scientific contributions, including a MacArthur Fellowship and the National Medal of Science. In 1997, Mike joined Microsoft Research and in 2005 became the director of Station Q, Microsoft's quantum computing research lab. As of 2023, Mike is a senior research scientist at the Center for Mathematics and Scientific Applications at Harvard University. Welcome, Mike. How are you doing today?
I'm great. Thank you. Nice to be here.
Yeah, it's such an honor to have you here. Maybe I'd just start out by asking you the following question. There are several examples of Fields medalists leaving mathematics, leaving academia. For instance, Grothendieck, who left mathematics entirely. Villani, who I believe is now spending all this time with French politics. But I think you're the only Fields medalist that I'm aware of that has left academia for industry. Can you kind of describe for us that experience and your thoughts on academia versus industry?
Sure. Yeah. Interesting question, Tim. Personally, I never left the academic mindset. I always followed, the idea of basic research and trusted that, something useful, even financially useful for a company would come out of, thinking through important problems. I did run into pushback when vice president told me that sometimes to ship the product, you have to shoot the engineer, by which he meant that a creative engineer is likely to come up with a better way of doing it every week and therefore never complete the program on any one of his ideas. And I think, that is a criticism. It has some domain of validity. I think industry also has a mindset kind of getting things done and being time efficient and focusing that is complementary to academic point of view. So I've enjoyed standing in both camps.
Oh, that's great. Do you, how do I say? I guess maybe you're obviously a special person, Mike. So maybe you've had more leeway, let's say, than a typical person. Do you have any, advice for young mathematicians today who are considering careers either in industry or academia?
Well, yeah, what you say is true. I used my privilege, if you like, when I was in industry, to cut out a space for myself. And I think there are good places to work. There are impressive research labs, that do allow a lot of freedom of thought. I mean, they have to maintain focus. So when they talk about academic freedom, it's usually within a scope, relevant to the problem that they hired you for, or the suite of problems. So I think a person needs to take that into account. And, it seems that whenever something is started, it's fresh and expansive, and then rules are added later. So I think a person coming into a situation has to sort of figure out where in the life cycle of the organization they're joining. Ossification does occur. Things start out creative and maybe eventually get less so. I remember my father telling me that's why there are revolutions, because laws are passed and they're never repealed, and rules are made, and eventually there are too many and there has to be a revolution. Of course, he was an old socialist.
I see. Yeah, actually, speaking of that, I was reading online that in your youth you were interested in painting, and in your family there are a lot of artists. Can you maybe say a little bit about the role of art and beauty in your
Yeah,
life as a mathematician? Yep,
my
and how
mother
it
was an
guides your
artist.
problems. Yeah, that you work on.
Yeah, thank you. Yeah. No, I've always thought of math as much more of an art form than uh, a technical domain. I mean, obviously, you need some technical power to pull everything together, but asking the right questions and following a path that's going to lead to something beautiful, to me, feels more like art. And it's going to be very interesting in this new age of artificial intelligence to see how that fits in. Maybe uh, maybe the last thing we'll be left with, at least for a while, as humans, is sort of guiding mathematics. With an artistic sense. Sort of getting the bot to calm down about what it's excited about and just say, well, thank you for mentioning that, but frankly, I don't quite understand this subject you've invented. But I think it would be a little more interesting if you could go in this other direction. So, maybe it'll be like, painting with a program rather than a paintbrush.
I see. Okay, great. Why don't we go ahead and maybe get started on the technical part of our interview? So I think today we're actually going to have a different format than the usual Cartesian Cafe format. You have a very nice whiteboard behind you, and so you'll be writing on that, and I guess I'll just be talking along. But let me just start by saying what I think is a good outline, a way to organize our interview. You've obviously had a very long an illustrious career in many different topics. And so I thought we could organize it chronologically, which is also roughly subject matter. So there's sort of, there's the early Mike, so to speak, in which you were a mathematician in academia, and you did incredible work in topology, which led to your winning the Fields Medal and the solution of the four-dimensional Poincare conjecture. And then, as mentioned in the introduction, at some point you left for industry through joining Microsoft and then working in quantum computing. So that would be sort of mid-Mike. And then now we have present-day Mike. And from looking at your recent papers, you've branched into some other areas like economics. And so I thought we could also talk about that. And so I think those sort of three pillars, early, mid, and present-day Mike, would be a good way to kind of give a nice panorama of all the things you've, or a small slice of all the things that you've thought about, and just to give a glimpse into the kind of work that you've done. How does that sound?
Yeah, it sounds fun. My life is flashing before my eyes, as they say.
All right.
Yeah.
Well, it's good to have this conversation with you and to celebrate the great work that you've done.
Thank you.
Yeah. Why don't we start with a formulation of maybe the four-dimensional Poincare conjecture in a way that I think, let's say, physicists or engineers or machine learning people, maybe at that level, that they could sort of appreciate.
Yeah, sure.
And the reason I want it at that level is that you gave a very nice lecture at Harvard recently where you kind of give it to a generalist math audience in some sense. So I think we don't need to go into that level of detail. I thought it was an excellent talk, and I'll link to that. So I think we can give like maybe one or two notches below that at a level where, say, my peers at Google might appreciate.
Great. Yeah. So, topology is about a whole lot of different things for different people. Some people are in function spaces and infinite dimensional topology, but there's a really strong core where topology means manifold topology. This is like the tradition of Riemann. So I was a Princeton graduate student, and I was raised in this, Riemann is God kind of thing. And I actually remember when I first saw Michael Atiyah as a youngster in Berkeley, one of the graduate students insolently asked him why he was interested in manifolds. So if you just imagine this, there's Michael Atiyah, there's some young graduate students saying, why are you interested in manifolds? And he was sort of dumbfounded. He had no answer for that question. It was, like asking the Pope, why are you interested in God? So, So anyway, that's the premise, and you want to understand manifolds. So manifolds are topological spaces that are modeled on Euclidean space. So they're glued together by patches. So it's a perfect instantiation of the idea of local to global. You have the simplest local thing that we all use and move around in all the time, Euclidean space of a certain dimension, and then you want to patch it together. So if you patch bits of plane together, you can get a surface. It's more esoteric if you patch bits of three space together. What kind of three-dimensional manifolds do you get? Like the three torus is the simplest one to think of, maybe the product of three circles among compact manifolds. So the question in every dimension arises sort of, can you describe the simplest closed manifold, which would be the sphere of that dimension, in terms of simple properties of maps? And this is called homotopy theory, of which maps can be deformed to points. Okay, so let me say the Poincare conjecture in dimension n. It says that a compact manifold of dimension n, so an n manifold, and I'll just write is for a moment, is the sphere Sn, if and only if maps from smaller spheres deformed points. Smaller dimensional spheres.
Yep.
So in the case of n equals 2, we're talking about surfaces, n manifolds, then n is 2 is a surface, and some simple surfaces, the orientable ones start like this. You have a two-sphere, you have a torus, you have a surface with higher genus, and so on. Well, what are the spheres of smaller dimension? Dimension 2, well, smaller than that would be dimension 1. So a one sphere is circle, often denoted S1. And suppose you take a map from the circle into the two sphere. Well, that's some curve like this. Maybe it crosses itself. You can map a circle into any of these surfaces. But the two sphere is picked out by the property that any way you map the circle in, you can deform the map continuously. This is called the homotopy. You can deform the map so as to shrink the circle until it's a point. So this test works for in this classical dimension. It's this final case, which was established by Perelman, 2003 and 4, that it's also true for the three-dimensional sphere, which was the original form of the Poincare conjecture. By the way, Poincare never really thought about the Poincare conjecture much because he stated it very carelessly and made a few, he stated it for homology instead of homotopy. And he left out, he only thought about mapping circles in his statement. He didn't contemplate that when you have a higher dimensional sphere, you should also consider maps of somewhat higher dimensional spheres into it. So the way he stated it, S2 cross S2 would have been a counterexample to the original statement of Poincare's conjecture in dimension 4. So it wasn't really central to Poincare's research. It's something he threw out there into just it. Okay, now I sort of slid over an important point, which is really important in 4 dimensions, where what does the word is mean? And the Poincare conjecture historically has been studied in 3 categories: smooth, piecewise linear, and topological. So all manifolds can be considered with varying degrees of structure. If you just take the simplest notion that you should have patches which are Euclidean space, that gives you a topological manifold. But if you require that the overlap of charts be by diffeomorphisms, they're glued together in a completely smooth way, then you have smooth manifolds. If it's piecewise linear combinatorial gluons, then you have PL manifolds. So there's some subtleties as you go from one category, as it's called, to the other. But in the case I studied, the four-dimensional Poincare conjecture, PL and diff are the same. So there are really two flavors. You're trying to understand whether topological manifolds are unique, given this very simple homotopy theory, or you could ask whether smooth manifolds are also unique with that homotopy structure. And that's still open. The smooth case is known as the smooth Poincare conjecture in dimension 4. And you might say it's the most important open problem in topology. But what I proved in 1981 or two, I guess, one, is that if you have a compact four-dimensional manifold such that maps from the circle and maps from the two-sphere into it can be shrunk to points, then that manifold is homeomorphic to the four-sphere. And the argument actually is a dance involving smooth and topological techniques. And the smooth techniques, most of them come from high dimensions. I should note as a matter of history that the high dimensional version is the easiest one and was solved first. So Stephen Smale, in 1959, proved the Poincare conjecture for n greater than or equal to 5. And the actual statement is that if the manifold has a smooth structure and this homotopy condition, then it's at least homeomorphic to the sphere of that dimension. So there's a slight loss of category, and it's famous that that's the best you can hope for in high dimensions because of Milner's exotic 7 spheres, which were found in 1957. So they're a group of exotic structures on the 7 spheres, cyclic group of order 28.
For people who might be new to this subject, there's a difference between being homotopy equivalent and homeomorphic, right?
Right.
And,
so I didn't. Yeah. So
is there a good example that we can draw just to kind of illustrate why this is like an actual theorem to be proved in some sense?
Yeah, okay. Yeah. So I skipped over the word homotopy equivalent, and I used an equivalent condition in the case of the sphere. And I said that maps of lower dimensional spheres could be contracted to one. That was my way of saying for non-experts that the manifold was homotopy equivalent to the n sphere. But nice way to state it, which is the way you stated it, is if a manifold is homotopy equivalent to the n sphere, it is also homeomorphic. Now your question is, give me an example of the difference. That's a really good question. And let me give you an example of two manifolds with boundary that are homotopy equivalent but not homeomorphic.
Sure.
Because that can be done with surfaces.
Okay.
And we have to go to four manifolds, but we'll come back to four manifolds in a minute.
Sure.
So for surfaces with boundary, we can just take this picture. We can just take, this is not a surface, well, this is a planar region, is what I'm drawing here. I'm just taking a disk in the plane with two subdisks cut out of it. Okay? And compare that to a torus, which I'll draw like this, sort of a horizon. That this is supposed to be a surface robustly in free space. And now remove a point. So remove a neighborhood of a point. So a torus with one puncture, you might call this D2 minus for the puncture. Okay, these turn out to be homotopy equivalent, but they're not homeomorphic.
Mm-hmm.
So both of them are homotopy equivalent to a wedge of two circles.
Mm-hmm.
This is really easy to see in this picture because homotopy equivalent is allows it. One way of getting a homotopy equivalent is what's called a deformation retraction, where you just sort of squash something down to a spine. And if you look at this wedge of circles, you can just squeeze that down to the circles. And actually, you can squeeze this punctured torus down to two circles also. Famously, it squeezes down to this circle. I have other colors here. So this circle union, this circle.
Yeah, it's easier to see that when you present the torus as a square with opposite sides identified, and if you remove the middle point, you could just kind of retract the interior onto the boundary, essentially.
Right. Yeah. So drawing the picture that way, we take a square and identify opposite sides. Sometimes people put little arrows like this showing how to identify.
Mm-hmm.
Then if you remove the puncture and you think of the puncture as now 4 little quadrants removed like that, now we describe the punctured torus the way you just suggested. And then there's this circle, which goes this way, and this circle, which goes this way. Is that the picture you wanted?
Yeah, sure.
Now,
I was going to remove the middle point, but okay, that's fine too. The corners are fine too.
Yeah, well, that torus is a group, so it's homogeneous.
Sure. Yeah, okay. Great. Yeah. I mean, so like intuitively, basically, homotopy equivalence means you could kind of squish one thing into another, whereas homeomorphism is a much stronger condition where you kind of have to, faithfully map one thing to the other. I mean, very intuitive.
Yeah, that's right. I mean, for non-experts, homeomorphism means that there's a continuous map that's one-to-one and onto. So the points are just bijected.
That's right.
Yeah, someone once asked me, how I proved the Poincare conjecture. I said, well, it's just a homeomorphism. I just had to say where every point went. And I
did. Okay.
So Smale proved that high-dimensional homotopy spheres are homeomorphic to spheres. And most of his argument, or a lot of his argument, works in dimension 4, but there's a technical difficulty, which I spent 7 years on, and I think maybe the publication date is 82, though the work was actually done in 81, or PC4. And just to give a flavor of why the high dimensional case is easier and what I spent 7 years working on is in high dimensions, Smale's argument works by analyzing a Morse flow on the manifold. So this is just like the way honey would drip over the manifold if you put it in a gravitational gradient. So, like picture a torus and, maybe standing up vertically. And there's with respect to the height function, there's a critical point on the top and it has a descending disk. The disk kind of descends like honey. And then at this critical point here, the disk would meet itself and its topology would change to an annulus. And you'd see this much. And then you keep going and the annulus would come and meet itself again and have a punctured torus and then a disk. So you can kind of understand the topology of a manifold patiently by watching it form as this gradient flow sweeps out more and more of the manifold. And, the form of this theorem is to try to align some algebra with some geometry with algebra, because, this homotopy condition is an algebraic thing. And what it's really telling you about is it's telling you about how descending manifolds from some critical points and ascending manifolds reversing the flow from other critical points all those manifolds cross each other. That's the boundary maps of the chain complex, which describes the homology of the manifold. And
yeah, just to clarify that point you just made. So this is kind of where geometry and analysis meets topology, right? Because with this picture you just drew, you can imagine sort of like water, instead of honey, I'll think of, let's say, water kind of flowing down the torus, and sort of at the top, it's sort of like, when there's like 4 special points in that torus you drew, right? Which is like the top and the bottom, and those 2 kind of like
right.
at the top and the bottom of the hole. And as water kind of goes down, it changes topology right before your eyes, because, between the top and the top critical point and the next one, sort of the water has a certain shape. And then when it flows past the second one, starting from the top, it sort of splits into 2 tubes. And then when it goes past the other critical point, it sort of reunites. And so you could sort of see how the topology of that water is changing, which is also kind of also the topology of the manifold itself, right? So sort of that's the sense in which the critical points are telling you things about the topology of the manifold. It was just
That's
restating
right.
what you just said. Yeah.
No, that's right. And actually, it's useful in this torus to think about this ascending descending manifold thing. So the descending manifold from the top is this circle. That's kind of the boundary of this growing disk of water or honey. And the ascending manifold from the next critical point, this one, because this is a lower index, its ascending manifold is one-dimensional. So it's coming up in the front and up in the back. And that intersection I was talking about is these 2 points. So if you look at those 2 points are telling you who are going to get identified when you cross. That's the pinch point. As this circle goes down, it's going to pinch and break. It breaks into these 2 circles. So if you watch this circle going down, what happens is it pinches, it becomes like a figure 8. That's the cross section right through here. And then the figure 8 breaks and it looks like that. It's called a Morse singularity. It's given by a quadratic equation. It's given by x1 squared minus x2 squared.
I see. I think what you're doing. I see. You're looking at sort of, how do I say, that circle you drew at the top, right? The boundary of the unstable manifold. You looked at its evolution under the downward gradient flow, right? And you're keeping track of that. Okay, that's right.
Yeah.
Okay.
Yeah. So anyway, that's sort of the flavor of Smale's argument, is to try to line up the geometry of these stable and unstable manifolds, which is a synonym for descending, ascending, to line up that geometry with the algebra of the chain complex. Okay? Because the chain complex kind of records the same information, not by drawing pictures, but just by writing down integers. How many times does one manifold cross another? Now, it turns out that at the key moment in Smale's proof, these crossing points, so say here's just in general dimensions, say this is the descending manifold, and say this is the ascending manifold.
Yeah. By the way, is it easy to say what the descending and ascending manifold is? I mean, I know what it is, but sort of for the people who are watching, is I don't think we properly defined it. Is there a simple way to say it?
I didn't define it. I mean, it's if you think of it in terms of this quadratic form model that I gave, it's some like coordinates x1 squared plus ... xk squared minus xk plus 1 squared minus xn squared. Then if you look at this quadratic form, it has 2 eigen subspaces. So there's an eigenspace of eigenvalue plus 1.
That's right.
an eigenspace of eigenvalue -1.
Mm-hmm.
So these would be the negative ones would be the descending directions.
Mm-hmm.
The plus one eigenspace is the ascending directions in this convention.
Yep.
And this is the infinitesimal version at the critical point. It's the decomposing the tangent space of the manifold at the critical point in directions which will turn up versus those directions which will go down once you integrate. So these are the ones that go up steepest. These are the ones that go down steepest. And then there's some kind of light cone between them, which are the ones that hesitate.
Mm-hmm.
So the ascending manifold was gotten by integrating this vector field, which is the gradient vector field of the flow. It integrates to a disk.
Yeah, maybe it's also another. This is equivalent to what you're saying essentially, but in terms of calculus, right? I mean, it's a critical point, so it doesn't have its derivative is 0 there, and so you basically only have the second order part, which is the leading part, and then you can choose coordinates where everything looks like a sum or differences of squares, and so you're looking at the Hessian essentially, and then it's just sort of the positive eigenvalue subspace will be. I guess depending on your sign convention, it'll be one of the descending or ascending, and then the negative one will be the other one.
Right. Yeah, I wrote that word since you don't have the.
Yeah. Okay. Yeah.
You're
okay.
right. Yeah. Exactly what you said. It's a second order thing, and maybe the most famous lemma is just. I think this one might be called the Morse lemma. Right. Is just what you said, that you can change the coordinates on the manifold is when the Hessian is non-singular in order to put it into this form.
That's right. And then at the top of the manifold, everything is negative, so it's descending. At the bottom, everything's positive, so there's the ascending. And then for the two ones in the middle, it looks like a saddle, so there's a descending and ascending direction. Right.
Yeah. And now the key point in this idea of you have algebra, which is coming from something called the chain complex, and you're trying to get this to biject with pictures. Mm-hmm. I don't know whether they're called topology or geometry, but it's like these pictures we're drawing. Okay, so what's the difference between the algebra and the pictures? The difference between the algebra and the pictures is that the algebra sees these crossings between the ascending and descending manifolds as signed quantities. Like in this picture here, this is actually a plus point and that's a minus point. They're not, and it's actually, in this diagram, it's maybe more convincing. I drew a black line, I drew a blue line, and they do cross in 2 points. But it's clear there's some sense in which they should have opposite sign, because I can deform, I can pull the blue thing down until they cancel each other out and disappear. So the point is, in the algebra side of things, you only see the integer. It's the signed sum of all these points. So on the algebra side, you'd see 0 for this picture because you'd see 2 points. On the picture side, you see 2 points. You don't see 0. So in order for Smale to line the algebra up, he had to show that if it's algebraically 0, you can deform the flow to cancel. And in order to deform the flow, he used what's called this disk here. It's called the Whitney disk, because Whitney had previously used this in 1940 to show that n manifolds embed into n space.
Yep.
Well, put his name up there, Whitney disk.
Yeah, maybe just to clarify what you just said. So the way you can see the plus or the minus, basically the 2 curves that you draw, you have to, choose let's say a direction of parameterization, right? And then you could essentially use, say, the right-hand rule, if you want, to kind of compute what the sign is, right? So sort of there's a sense in which the first crossing has one sign. If you say, put your take the cross product of the 2 vectors.
I agree with this right-hand rule, but but let me argue that it's much simpler to see that they have opposite sign than to figure out what sign either one has.
Oh, I see. Okay, sure.
It's kind of obvious that they have opposite sign because they're trying to cancel.
Yeah. Okay, I see. And then that brings me to my next point, which is what you distinguished was what people will say is the algebraic intersection number versus the geometric intersection number, right? So sort of the geometric intersection number is the literal intersection of the 2 points, but sort of the algebraic one is the summation of those with signs, right? So sort of there's 2 intersection points, but really they should count as 0 because you could just slip off the 2 and it would be 0 after you do that.
Yeah, so we're now very near the punchline of why Smale's proof didn't work in dimension 4.
Mm-hmm.
It's because the workhorse for the proof in terms of lining up algebra to pictures was this embedded disk that you can find by whenever you have a plus point and a minus point on the level set. This is a picture taken in the level set with ascending and descending manifold. You have to, if you see a plus point and a minus point, in order to try to remove them, you want to find this embedded disk and use it as a guide to push one manifold across the other. And the problem is 2 plus 2 equals 4. The disk is 2-dimensional. It's sitting in a 4-dimensional space. If you're trying to prove the 4-dimensional Poincare conjecture, you're considering Morse functions relating a standard sphere to the homotopy sphere. So in order to prove the 4-dimensional Poincare conjecture, you're actually thinking about Morse functions on 5 manifolds. The cross sections are 4-dimensional. So the cross section in which this picture is taking place is 4-dimensional, and you see a surface, a disk, and you may see another sheet of the disk crossing.
Sorry,
so let me make it simpler.
How did you? What is the 5 manifold under consideration when trying to?
Well,
prove
yeah, I mean, I'm editing the argument, but I didn't explain the 5 manifold. But if you have a homotopy sphere, we call it semaphore, and you have the standard sphere.
Mm-hmm.
Maybe draw this one a little wiggly since it's only a homotopy sphere.
Mm-hmm. Mm-hmm.
Then there's a notion of cobordism between manifolds. 2 manifolds may be jointly the boundary of some manifold of one higher dimension. Mm-hmm. And it's a problem that was worked out in the 1950s by René Thom, which manifolds are cobordant to which other manifolds. And that's now within homotopy theory. So just the homotopy information that this is a homotopy sphere is enough to construct some cobordism connecting these 2 manifolds. And then the cobordism is simplified to what's called an H-cobordism, which means each end includes as a homotopy equivalence. So it's like factoring the original homotopy equivalence through a 5-dimensional manifold. That's the way Smale begins. And then he proves that this 5-dimensional manifold eventually has a product structure on it. And that's, that's how he proves that this is homeomorphic to that. Mm-hmm. But in order to get this product structure, the product structure is accomplished by canceling the critical points. You see, these maneuvers we're doing, like trying to slide the ascending manifold away from the descending to cancel these points. If you remove the excess intersections between ascending and descending manifolds, then if the chain complex algebraically cancels, then the geometric thing will have no critical points.
Mm-hmm. By the way, so what Smale proved was the version where the sigma and the S are 5 manifolds, right? Now we're trying to do the 4 manifold version, the one that you wrote there, right?
Yeah. So I'm showing. I drew this picture to illustrate where Smale's argument runs into trouble in the 4-dimensional case. Mm-hmm. The way it runs into trouble is this 2 plus 2 equals 4. So this is a little bit of general position geometry. So let's just think of a simpler formula: 1 plus 1 equals 2. Mm-hmm. What does this tell a manifold topologist? This says that if you just draw randomly an arc in the plane, it'll cross itself, because you have a 1-dimensional sheet of the arc and somewhere else another 1-dimensional sheet, and the linear model of subspaces intersecting in a higher dimensional vector space tells you that generically intersections of two lines in the plane can't be removed by some perturbation. Whereas if you had two lines in free space and they happened to cross, you could move one line slightly and they wouldn't cross, right? So it's a similar thing here. The Whitney disk is two-dimensional. So an additional bit of it, another sheet of that Whitney disk, like a neighborhood of two different points, if they happen to cross each other, that'll be a stable situation. You won't be able to remove it by perturbation. So the only reason we knew there was a map of the disk here was some homotopy information, like something being simply connected. But that homotopy information is not going to help us with this deformation. You need it to be embedded in order not to wrinkle up the ascending manifold as we push it.
Yeah, actually, one point of clarification. So I understand that 2 + 2 = 4, although in this cobordism, that manifold boundary is 5-dimensional. So I'm a little confused when there's 5 and 4, because if you're doing Morse theory on this 5 manifold, aren't you going to have a 2 and I don't know. There's a 5, right?
Well, all the interesting activity is taking place in a level.
Okay, that's what I probably thought you meant. Okay, yeah. So once you restrict to a level of a cobordism, then you have the 2 + 2 = 4 problem.
Yeah. So maybe maybe I should be more sophisticated and write 2 + 2 = 5 - 1.
Okay, all right. That answers my question. Okay, great. Okay, all right. Just like in your picture with the torus, you're looking at the boundary of, say, an unstable manifold. That already gives you
that's right.
the codimension 1.
The boundary of an unstable manifold meets the boundary of a stable manifold.
Got it. Okay, there we go. Yep, got it. Okay.
So, so let me erase this, if that's okay.
Sure. Yep.
Let's tell you what we do with this problem. So, the mathematician Andrew Casson in 1973 produced a beautiful infinite process, which he was thinking about this problem of getting this disk in there, and he figured out that, well, you can't get the disk embedded, it crosses itself. So this is a low-dimensional picture of the disk crossing itself, okay? So what I literally drew is an arc in the plane, but think of this as a disk in a 4-manifold that has one transverse double plane, okay? And it might actually cross itself many times, Right. But Casson was able to produce a process where then you look at these loops that were created by the self-crossing, and he was able to add another disk which killed those loops, but these disks also crossed themselves. Now, if you ever kind of added disks that didn't cross themselves, you could maybe unwind the whole picture, get an embedded disk. But unfortunately, things didn't get better. They just stayed the same as you progressed in this process. So what he found is that it was possible to create an infinite construction. It looks like spaghetti. It just gets messier and messier. And basically said, well, can we do anything with this? And, I was young, so I had low opportunity costs as a 23-year-old mathematician. So I just thought about this Casson's construction for 7 years. And eventually I found you could get some kind of geometric control over it. So because what we want. So Casson left us with this big mess of spaghetti, disks on disks on disks. And we just want one disk, but we want that disk embedded. We don't want it to cross itself.
By the way, is there a version of this for, because you're how do I say? I'm trying to think, like, because you're doing your picture is a dimensional reduction where you're thinking of 2 as 1 or something like that. Is there
exactly
how would I is there an analog of this that is faithful for like the picture you still have, I think, which is the disk, the sort of the disk allowing you to slip a curve off another curve? Can you is there a way to draw what's going on in that example? Yeah, kind of that example to your right. What would be the analog of these?
Oh, well, I mean, the way I would draw it here is I would say, here's the boundary of the disk we want to find.
Mm-hmm.
But instead of finding an embedded disk, we find this thing.
Mm-hmm. Mm-hmm.
But it's an implicit picture. I mean, it's not literal.
That's right.
I'm drawing it like you have to know which lines in the picture are one dimensional and which are.
Yeah. That was what was a little jarring a little bit. Yeah.
I mean, there is a way of making these pictures rigorous with
Mm-hmm.
time evolution conventions.
Okay.
So like in my book with Frank Nguyen, we draw a lot of pictures like this that have some statements below the pictures about like which bits evolve in time and which bits are just snapshots. So like, for instance, if you want to know a convention like that, suppose you want to draw a rigorous picture of two disks in floor space meeting in 2 points of opposite sign. So in the book with Frank, we might draw something like this. So, but then we'd have some like we'd write down underneath. We'd say the horizontal disk only exists at time 0. The thing that's drawn at an arc is a disk which persists from time -1 to +1. Does that make sense?
I think I see what's going.
If you add a fourth coordinate, so it becomes now a movie.
Yeah.
If it's a movie, then this one disk just flashes into existence at a single frame of the movie.
Yeah.
And this arc is present throughout the movie.
Yeah, I see what's going on.
Then I think you rigorously have draw. You can make a rigorous picture, but
that's right.
Actually, these non-rigorous pictures are actually cute and have a lot of meat in them, a surprising amount. Like, let me just show you something interesting. When you have a crossing point like this, you can draw 4 points, 1 in each quadrant. What is that? That's a representation of the Clifford torus. In floor space, the product of 2 unit, if you think of floor space as C2, you can think of the torus, which is the product of the 2 unit circles.
Okay.
In the coordinate factors. That's called the Clifford torus. Okay. And it kind of links the 2-dimensional axes, if you like. It's 2 directions linked to 2 axes.
Okay.
So if you want to picture the Clifford torus, which sort of envelops these double points, you can actually see it quite clearly in this cartoon, one-dimensional cartoon.
Okay, maybe I'll think about that.
And 4 points. 4 points is not a coincidence. 4 points is the zero torus. Well, it's the product of 2 zero spheres. Because a zero sphere is 2 points, right?
Yep.
The unit sphere in the line is +1 and -1. It's 2 points.
So
the product of a zero-dimensional sphere with itself is 4 points. So it's quite a faithful picture. In fact, a lot of what I did, like in those 7 years when I was playing around, is I made like a library that then became very natural to me. I could look at all these crazy pictures and I could know what was real and what wasn't.
Okay. Great. Anyways, this is maybe a bit of a digression, but please continue with your Casson discs.
Yeah. So anyway, I did a lot of work on these, and one of the things I eventually was able to obtain was geometric control. So these higher and higher stages became smaller and smaller. Like as you said, we shouldn't recapitulate the whole proof.
Yeah, of course.
What I wanted to give a hint about is we've talked about the H-cobordism theorem and Morse theory and surgery theory comes in. So we've talked about how like smooth manifold techniques are like one side of the story. But the big question I think that people should have in their mind is how come when you succeed in this, you only show that it's a homeomorphism at the end, rather, where did you lose differentiability?
Sorry, did we finish what was the punchline? So you had all these disks, and then I think, I don't know if we said at the punchline yet, something magical happens.
I said I made a lot of progress over those 7 years with this spaghetti, with the Casson handles.
Yep.
And one bit of progress is geometric control.
Oh, I see.
Geometric control meant that the size of these stages became smaller and smaller and smaller.
Okay.
So there was a limiting process.
Okay.
Okay, and then understanding these limits got you into point set topology. You left the world of manifold topology. And that's and you run into strange beasts in this world. Like, I don't think that more than 10% of mathematicians know there's something which is called a manifold factor. Let me test it on you. A manifold factor is a topological space that is not a manifold, but when you cross it with R, it becomes a manifold.
No, I did not know about that.
Isn't that astonishing?
Yeah, I can't even visualize what that would look like.
Well, I'll show you an example, and it's actually related to the Casson handle.
Okay, sure.
So if you take the simplest Casson handle, the one that doesn't branch, but with geometric control, so these things get smaller and smaller, then if you have a handle, there are two bits of the boundary of the handle. Let's do the dimensions we have here. So this is a 2-disk. Then this bit is, this bit down here is S1 cross D2. This is a solid torus. This is 1/2 of the boundary. This is called the attaching region of the handle. And then the dual region is D2 cross S1. And that's sometimes called the belt region or the cochord. Now, if you take this crazy Casson construction with geometric control, and you take some kind of neighborhood of it, okay? You have something that looks like kind of a crumpled handle. Homotopically, it's a handle, but it's kind of crumpled. And it turns out that this region, there's nothing wrong with this. This is still S1 cross D2. This region is a manifold factor. What it is, it's S1 cross D2 modulo the Whitehead continuum.
Sorry, what are you pointing at? That arrow? I don't know what you're actually.
That arrow is the other region of the crumpled crumpled exterior. So this was the uncrumpled thing. Its boundary is a 3-sphere, right? This is a 4-ball, D2 cross D2. Here's D2 this way, and D2 also going this way, right? And the boundary the boundary of D2 cross D2 by the Leibniz rule.
Yep. Oh, I see. Yep.
Is S1 cross D2 union D2 cross S1.
I see. So one of those factors.
So that's what I wrote here.
Okay, I see.
But if the handle has been in a car crash, and it looks like this. It's all wrinkled and bent and crumpled. Well, nothing's gone wrong with this region. This part wasn't impacted. This is still S1 cross D2, the attaching region.
Yep.
But the pinch regular neighborhood out here turns out to be a very exotic object that doesn't exist in manifold topology. It's something in the world of decomposition spaces. So decomposition space theory is often interesting examples are made by taking some closed subsets inside a familiar space and declaring each of those to be points. And then you give the whole thing the quotient topology.
Remind me what the Whitehead continuum is?
Yeah, I'm just about to.
Yeah.
I'm gonna draw a picture of it. So here's the solid torus. And now the Whitehead link is this thing that's geometric degree 2 algebraic 0. So I'm going to put another solid torus in. this is a neighborhood of the Whitehead curve.
Hmm.
Is that visible in there?
Yeah. Uh-huh. Mhm.
Okay, so now, but let's keep going. Imagine inside this solid torus, you put another Whitehead curve.
Oh, I see. Uh-huh.
Okay, so this would kind of go around 4 times.
Yep.
And then inside that, you put another one, we go around 8 times.
Mm-hmm.
So the Whitehead continuum is by definition the intersection of I equals 1 to infinity of these solid tori. I'll just call them T sub I.
Ah, okay.
Where T sub I plus 1 contained in T sub I is this Whitehead pattern.
I see. So it's this infinitely thin but twisted thing.
Yeah, it's getting thinner and thinner and thinner. And it's actually sort of in some homotopy sense is like a point. It has this what's called the shape of a point. Because the way to understand this is each of these embedding one into the next is degree 0. So the infinite intersection shouldn't capture like any of the Czech homology of the circle or of the solid torus. It should slip away, right?
Okay, I haven't thought about this in a long time, so I'm not sure what that.
Well,
that
think of this like an inverse system, and all the bonding maps are 0. It's like you have Z, Z, Z. These are the integers, like first homology, and each of these maps is 0.
Okay.
That's what's going on homologically with this construction.
Okay.
So the reason I point this out is homologically, you shouldn't think of this crushing of the Whitehead continuum to a point as doing much damage. It's leaving the homology of the manifold basically the same, even though it's not a manifold anymore.
Okay.
And it's giving this, anyway, you can, by direct calculation, you can see, it turns out that each of the stages, I said this was made by infinitely many stages. Each stage is one of the complementary regions, the solid torus union, the next subsolid torus.
Okay.
The choo-choo train, you stack these complementary regions together infinitely. And because they're getting smaller, it's equivalent in the end to crushing the infinite intersection.
Okay.
So anyway, that's like the non-manifold side of topology that comes in to analyzing this. And as I was saying, the astonishing fact is that this thing here, the solid torus modulo the Whitehead continuum, is a manifold factor.
Okay. Is that hard or easy to prove?
It's a beautiful theorem from the 1960s in the Bing School of Topology, and I shouldn't try to prove it to you, but it's a shrinking argument.
Okay. So, in interest of time, I want to kind of wrap this up. But so once you so geometric control is kind of knowing this limiting behavior. Once you know that it's a manifold factor, I guess is there like a last step or two, and then voila.
Well, this is this. You say, what was I looking for those 7 years? Try to replace the step that Smale would be missing. I was looking for an embedded disk. And if the boundary of this thing had turned out to be just S1 plus D2 without this quotient, then I would have had the embedded disk. I could have just used any one of these D2 factors in the boundary. Well, the fact that this thing is a manifold factor is extremely encouraging, because it means if this wiggly thing had a product neighborhood inside the 4 manifold, then that would undo the badness that was created by dividing out by the Whitehead continuum. You see, the Whitehead continuum, when you divide out by it, destroys the disk that you want to use, the disk in the solid torus, because the Whitehead continuum meets this disk in a Cantor set. You can see that, right? Because it's 2 disks, then 4, and so on. So the thing that I was hoping to be an embedded disk is actually compromised. It's an embedded disk modulo Cantor set. But if you could use like the normal region and the manifold factor property, you could sort of fluff it out and get a disk. Well, it turns out this does not have a product neighborhood, so that naive strategy is insufficient. But I would say this kind of gets you over the hump. This is where you realize that there's some hope of topologically finding a disk where smoothly it doesn't exist. And I should say, I went in kicking and screaming into the topological category. I didn't want to be there. I had no training, no knowledge, but it was necessary to follow the argument. And for a month or two afterwards, I hoped I could remove all these infinite processes and get a nice, understandable argument in the smooth category. But then Donaldson came along, Simon Donaldson, with gauge theory, and proved that many things were false in the smooth category that I knew to be true now in the topological category. So there was this beautiful fortuity that in 1982, both the infinite constructions were under control and gauge theory proved they were necessary.
Wow. Yeah, that is beautiful. I mean, that's a whole another conversation we could have, but just to wrap this up. So I guess can you say a word or two how you ended up getting that disk from this manifold factor if it was not this normal construction? Is that simple to say? Or
I think that people should look at the Harvard lecture. I mean, it turns out that I didn't look at just one neighborhood boundary, but a whole Cantor set worth of neighborhood boundaries that were my substitute for the manifold factor idea. That is, a manifold factor, what's happening with the manifold factor is it's saying if you had a continuum many of these things in a stack, the difficulty could be removed. Okay, that's what was known in the mid-60s. But I didn't have a continuum, but I had a Cantor set worth of them. The Cantor set is not so different from the continuum. If you take the middle thirds of the Cantor set and push them to points, you turn the Cantor set into an interval. That's a beautiful example of decomposition space arguments. You push the middle thirds, the Cantor set is stretched out to the interval. So that was sort of the inspiration. On a technical level, there were many things to do, but I think seeing this manifold factor is what makes you not give up.
I see. So okay. So is this the very core story then? Essentially, you have let's start over. So sort of you have Smale's work using getting us to get an H cobordism between the candidate 4 manifold and the 4 sphere. You use Morse theory to realize that the problem boils down to handle cancellation, and then because of 2 + 2 = 4, it's not so easy to do. That's really the main obstacle. And then by this technology of adding all these Casson disks and going down that rabbit hole, you finally find your canceling disk at the end of this long journey. Is that the
That's
summary?
right. Yeah,
Okay.
that's the summary. And because the canceling disk is only topological, when you deform the ascending manifold across it, you lose the smoothness of the Morse law.
I see.
And that's why at the end of the day, it's only a homeomorphism.
Okay, great. Does this cover kind of what you wanted to say about Poincare? I mean, I know we have other things we wanted to go to. So I don't know if this is okay.
Yeah, no, I think it does. Yeah.
Okay, maybe just one last thing, just for history's sake, because I know a book recently came out that kind of, I guess, talks about the details of this stuff, and I kind of wanted your thoughts because, so I guess you wrote your proof, I guess at the time, and for a long time, in fact, maybe there were very few people who actually understood the proof, and that was kind of why this book was written. Can you kind of walk through the kind of sociology of sort of writing down the proof, people not a lot of people understanding it, but of course, enough people understanding it to award you the Fields Medal in particular, and then kind of many years passing by until enough people sat around. Like, what can you? Yeah, I'm just curious about that. That's a very kind of peculiar sociology, right?
It's an interesting story. I mean, I think I'm partly to blame. Maybe wholly to blame. I grew up in a culture really where math was a verbal process, and explaining the proof to Dennis Sullivan was much more important than writing a paper that anyone else could understand. I mean, I just I don't know if it's generational or the subculture I grew up in, but it was the blackboard talk that was the standard. So I never really paid much attention to the quality of exposition, and it wasn't good enough. Now was partly repaired by the book I wrote with Frank Nguyen a year or two later, and we gave a summary of the proof. But even my original paper plus the book, I'd say that only the generation of topologists that had watched me lecture knew the proof. Well, actually, when the proof was finished, I went to Texas, which was the hotbed of this Bing topology. R.H. Bing was still there. And I lectured for like 20 hours on the proof. In fact, I'm a marathon runner, but my feet were crippled after the lecture.
This is one lecture, one day, 20 hours? Or
No, I was there for a week.
Oh, okay.
But during over 5 days, it was standing at the blackboard for on the order of 20 hours.
Okay.
And it was interesting because in the audience, there was Andrew Casson, and there was R.H. Bing, and there was Bill Eaton, and there was Mike Starboard, who I've worked with recently. And I felt that no matter what I was saying, there was someone in the audience who knew more about it than I did. I was never the expert. So there were always interruptions and interjections, and no, you should do it this way and that. And, so it was very aggressive. But when we were done, I felt like everything had been covered, to the last detail. That was sort of the end of it for me emotionally. I went to Princeton and gave some talks, but no one there really followed the details. But anyway, so it turned out that Peter Teichner, who's a longtime friend of mine, was organizing a group of students and postdocs to go over and try to make a modern rendition of the proof. And I got a little bit involved with the project. I gave, I think, 10 lectures by TV, closed circuit TV from Santa Barbara to the Max Planck Institute. And that was sort of the beginning of the project. And then it took like 7 or 8 years, maybe 8 years for them to write the book. And I looked at it and it looks great.
What's the timeline? So you got the Fields Medal in '86. You went to Microsoft in '97.
So the proof was in I wrote the proof in '81 or '82. And yeah, the Fields Medal was '86, and the book with Frank was probably around '90. And then but you said it was still not quite satisfactory based on the community reaction, I guess. And then only this, like a year ago, that this other book came out to finally kind of but the project to write that other book is like a 10-year project.
I see.
8 or 9 years. So I mean, the reason this is hard for people to learn is you have to think about things that you won't ever run into again if you're an ordinary manifold topologist. I mean, you have to think about these manifold factors and decomposition theory, shrinking homeomorphisms. You have to invest some time to get comfortable with this sort of layer of topology below manifolds. It's like metric spaces, it's a little bit like Perelman's history in a way. I mean, Perelman's proof was completely different, based on PDEs. But one of the things that enabled him to succeed is he had made himself the world's expert on Alexandrov spaces. And he realized that he didn't have to do all the analysis that Hamilton anticipated would be necessary to prove the three-dimensional Poincare conjecture using the Hamilton equation, Ricci flow. So Hamilton, is very much a purist, and he sort of wasn't interested in just a proof of the Poincare conjecture. He wanted the proof, which involved analyzing all the stable or the stationary phenomena. He wanted to find, the long-lived, the infinite history solutions. He wanted to classify the singularities, basically. And Perelman realized, he kind of went to the juggler. He realized you didn't have to finish the analytic program. You could start and stop it. So that's why he introduced, these surgery steps in the middle of the analysis and then return to the flow. So I'd say in that regard, this four-dimensional proof has a similar feature. It doesn't use Alexandrov spaces, but it uses decomposition space theory. But in both cases, this understanding, you need an understanding of things that are less than manifolds.
I see. Okay.
And most people don't want to take a year out of their life to get an intuition for things that aren't manifolds. Like a Tia never would have.
I see. Okay. Maybe this is a good segue to your kind of second career studying quantum computing. I guess I'm curious. Yeah, maybe you could give some more biographical detail. Sort of. I guess there is in another alternative universe. Maybe Mike could have spent years of his life just writing out the proof carefully, but I don't know. Were you kind of like tired and kind of like I need something new, and so quantum computing came along? What was?
I can actually tell you the history there is pretty interesting. I'll just sit down for a moment, change the focus here. So I went to Harvard to visit in 1988, and Cliff Taubes and Raoul Bott asked me if I'd participate in a seminar that they were going to run on a paper of Ed Witten's. This is his famous paper where he explains the Jones polynomial as quantum field theory, his SU2 level K quantum field theory. And I didn't know who Witten was, and I didn't know anything about mathematical physics. And I was amazed. I was just completely blown away, and I decided I wanted to learn physics because here was this guy who manifestly from his first draft, which we had, did not know much topology, but he had completely cleaned the clocks of the topologists by having this tool of quantum field theory under his control. And I thought, okay, I want to learn this. So the other thing that happened that fall is I learned about this work from Jaeger and some collaborators in computational complexity, which showed that approximating, that the exact values of the Jones polynomial as algebraic numbers was sharply hard to compute. So I had these two things going on in my head in 1988 at this Harvard seminar. One, and I barely even knew what Whitney was saying in the paper, but he says in the introduction, he says, the values of the Jones polynomial, these roots of unity, are the expectation values of certain quantum field theories. And then I had just read that the computer scientists had figured out that these were sharply hard to compute. So the thought was inescapable. Why don't we build a machine, a computer, that could reveal these expectation values, and then we would destroy Church-Turing thesis. We'd have a shortcut to sharply hard numbers. So I was enthralled by this, and I went to Cliff, who's well-educated in physics. I asked Cliff Taubes about this, and he said, "Well, don't get too excited. What Witten calls physics is not what you learned in high school, and that there's no real-world realization of these quantum field theories. They're they don't have any matter in them. They're very exotic things." So I was kind of discouraged for a while, but in fact, it's funny. I thought, eventually it turned out that the way to try to get into topological states of matter and these quantum field theories is through cryogenics, which we can talk about in a moment. But I didn't know about that. I didn't know about the quantum Hall effect when I was at Harvard in '88. And all I knew is that it was SU2. And I knew the standard model, at least vaguely. So I thought we'd need the weak force to make a quantum computer. I didn't know about effective field theory. So I thought to produce Witten's SU2 level K, we might need a nuclear weapon or something.
Sorry, just to back up. So I don't know off the top of my head what P sharp is, but it's some complexity class that I guess
it's accounting. It's like instead of asking whether a KSAT formula has a satisfying assignment, which is like the canonical NP complete problem. If you ask how many satisfying assignments does it have, so the answer is an integer.
I see.
That's the canonical problem for what's called sharp P.
I see. And so
it's the counting analog of NP.
I see.
So these evaluations are sharp P hard. It turns out that's a slight irrelevancy because like a physical device is never going to tell you the algebraic integer. What it's going to tell you is an approximation to it. So it's a further fact from computer science, which wasn't known until later. In fact, probably co-authors of mine and I had something to do with clarifying this. But the important fact is that approximate evaluation of Jones polynomial at roots of unity up to an additive error is BQP complete. It's not NP complete, but it's the guts of what a quantum computer can do.
Was the reason to go into quantum computing because you thought that quantum computing leveraged special computation such that it would be their quantum leverage, so to speak, would enable efficient computation of these Jones polynomial invariants, which would sort of be a huge contribution to topology.
Well, no. Let me say it a different way. So in '88, I'd never heard of quantum computing. And my idea was very simple. It was simply that Whitten is saying that something that the computer scientists say is hard to compute is an expectation value of something, X, a quantum field theory. So I was just sort of fishing around saying, can't we build something where we can measure this value? And within about 4 years, actually, physicists were starting to think of systems that could do this. There were papers written by Moore and Reed that quantum Hall systems at 5/2 Stilling fraction might represent Ising anyons, and at 12/5 perhaps Fibonacci anyons. So there was some idea that these expectation values might be, in principle, something that one could approximate by an experiment that you could do cryogenically with a quantum Hall fluid. But what is a computer? I mean, a computer is nothing more than a physical experiment with some easily controlled knobs.
I see.
So if you think that these are experimentally accessible, then you start to think, that the Church-Turing thesis is wrong. But it took a long time for me to learn. It wasn't really until 2000 when I was up in Microsoft, maybe 1998 or something. And I was at Microsoft already that people started asking me, isn't what you're talking about something like quantum computing? And I said, well, what is this quantum computing? And I think actually Dorit Baranov was visiting as a postdoc at the time. And I said to her, oh, no, this is much more interesting than what you just showed me, quantum computing. This is quantum field computing, So I said, oh, this is great stuff. And she said, do you think that's really any stronger? And I said, well, sure, it should be stronger because infinite dimensional Hilbert spaces and all this. But I think she put the seed of doubt in me. And then, with co-authors, Alexei Kitaev and Zheng Hong and Mike Larson, we eventually proved that the two were identical, that there's a polynomial time translation between this sort of Jones polynomial evaluation, quantum field computing, and the circuit model.
I see. So I guess maybe to go back about your motivation. So I guess Witten provided the link between, let's say, physics and the Jones polynomial, and the Jones polynomial is related to topology. And you as a topologist thought, oh, now I can somehow, instead of using my mathematical toolkit, if I had the right computational system, as it were, then I could sort of compute these topological invariants. Is that maybe a way to say
there are two links. I mean, there are two sides of the bridge. One is that Witten said that Jones polynomial, which I was favorably inclined toward as a topologist, but that's not the main point. He said the Jones polynomial was quantum field theory, and the computer scientist Jaeger and company said that the observables in quantum field theory can't be computed efficiently classically.
Okay.
So that means something's an observable in a theory, but the observable is extremely hard to compute. Then you naturally wonder, can you manifest that theory with a device so you can skip the computation?
Or the classical computation, that is.
Yes, yeah.
I
Do the
see.
computation by an experiment instead of numerically.
Yep. Okay. And then also, okay, I think I understand now. And then there was this comment you made about this would, violate or be a contradiction to the Church-Turing thesis. I'm actually not so sure about that. I mean, how do I say? You could always simulate a quantum computer classically, right? Just by brute force in some sense.
Right. So, this is the. I'm sort of following Scott Aronson's line here. You're right. The Church-Turing thesis got its name in the era before computational complexity, when it was simply a question of computability. But I think by 1970, people had already started to morph and use that same phrase, the Church-Turing thesis, for the computational hierarchy. That is, so what I meant by the Church-Turing thesis, which I think of as like a modern twist to it, is that up to polynomial equivalence, all practical computational devices have equal power.
Oh, I see. So there's the original.
It's a polynomial. The original Church-Turing had nothing polynomial in it because it's before the hierarchy.
I see.
But I meant that like a one tape and a two tape Turing machine are equivalent polynomially. There's like a quadratic slowdown when you go to one tape.
I see. Okay.
So that was widely believed by computer scientists until the advent of quantum computing. And then it was basically Shor's algorithm that, or maybe its precursor, there's a Z2 precursor, but those algorithms made people think that quantum computing had more, allowed super polynomial speedups to problems that involve Fourier transforms.
When did Shor's result come out? Was it also I think it was 94-ish or something, but it was a few years after the Jones polynomial, right? So you didn't have the luxury of that.
Yeah, that's right. That's right. It was 90. Yeah, it was 95, I think. But it was known that. But it was known in '88 that the evaluations were, as I said, sharply hard. These were the things that you were at least approximating in this field theory.
Okay. Anyways, so thanks for the history. So I guess you're this is the early '90s now, and it's like this thing seduces you away from Poincare, and now you're off into a new field.
Yeah, well, I mean, so basically that's the reason I left academia, is because in academia you have to kind of carry your graduate students along with you, and I felt like I didn't know enough to train graduate students in computational complexity and quantum field theory, which is what I was now studying. And the problem hadn't come to a head, but I had some former students who were working for Microsoft, and they asked me if I'd come up and give a lecture, and I just came up and gave like an academic style lecture. And Nathan Myhrvold was in the audience, and he just on the spot offered me a job, which kind of surprised me because I thought he'd say, well, I have to take it to the dean and we have to build a file in a case. And he just said, no, I make the decisions. You can have the job if you want it. And I was kind of impressed by how fast things could move. So I took it.
Oh, that's great. Oh, wow. Okay. So serendipity, as it were. And so, and then was there a Santa Barbara office at the time or did?
No, I spent 7 years up in Redmond and really enjoyed it.
Okay.
I loved the Cascades, the mountains. Yeah, it's funny. One of the things I stipulated when I took the job was, this goes back to the privilege we were discussing at the beginning of the segment. As I said, now, I really don't want anyone to bother me while I'm working. So after about 7 years of not being bothered, or 6 or 7 years, I was feeling lonely. And I went to Craig Mundy, who was the vice president for research. And I said, there's something you should know about. It might be possible to build a quantum computer using topological principles, using anyons in topological phases that maybe we could manufacture in a dilution refrigerator. I just thought he should know that, there was this possibility. And he became very excited about it. And we talked, and eventually we decided to create this Station Q in Santa Barbara to do the research. So moving to Santa Barbara was sort of a cost savings idea that, we had to build up this large physics group, but the question was, could you recruit the right physicists without proximity to a first-rate research institution, where they could just walk over and go to the seminar, so go to the colloquiums on Thursday. So,
So I see. So before,
why not co-locate with KITP here in Santa Barbara?
Sure. So before Station Q, you were working on quantum computing stuff, but not topological aspects yet.
No, I think I was. Actually, Alexei Kitaev was one of my first postdocs at Microsoft, so I was, we were definitely, no, it was more that I was doing it as sort of I was thinking about a lot of things, topology and quantum computing and the relations and the quantum field computing. I was thinking about all these things, but I wasn't thinking programmatically. Like I wasn't thinking like a business person. Like, how do we? I was just thinking as a mathematician that what's interesting, and it took me about 6 or 7 years to think. Oh, I should tell a vice president who has a lot of money, influence, that there's something that might be possible. And I wasn't even angling for like an institute. Actually, it's funny when he listened to me. He says, Greg, he says, so you want me to create an institute for you down in Santa Barbara? Is that what you're saying? And I said, well, let's call it a station, not an institute. To make people think of like the ice stations on Antarctica. Like we'll go where it's necessary to do the research,
Sure.
Not worried about the weather one way or the other.
Sure. Although it's of course very nice weather in Santa Barbara. But anyways, why don't we? Can you give like a quick overview of what topological quantum computing is about? Some of its highlights. Scott Aronson was a previous guest, so we've already had a crash course on sort of vanilla quantum computing. I don't really know anything about topological quantum computing. Can you kind of maybe state roughly what the I don't know, foundations are, and maybe some of the milestones and where the field is now?
Actually, let me say what the kind of very basic idea is, and then maybe give a topologist segue into it that actually echoes some of the four-dimensional discussion that we had. Yeah, so there's this idea of a TQFT, topological quantum field theory, which maybe, just to wrap it in its topological package, I'll explain in terms of the Atiyah axioms. So, and let's just do the case which is relevant, potentially relevant to quantum computing, which is called 2 + 1 dimensional, meaning 2 dimensions of space and 1 of time. So the physical material would be a surface, or a little, actually it would be probably in an actual case, it'd probably be a 2-dimensional electron gas sandwiched in a crystal interface between 2 semiconductor crystals. The gas of electrons is trapped there by potential barriers on each side. Maybe it's subjected to a strong transverse magnetic field, and these electrons organize themselves to minimize energy. And it turns out with suitable parameters, these energy minima seem to realize topological phases. So that's where the 2 comes from if you want to think experimentally. But if you think more abstractly, what the Atiyah axioms are basically that you have a surface. So in pictures, you have some surface, sigma surface, and then you associate to it a Hilbert space, is V of sigma.
So in what you just said about topological phases, should I think of how do I say how do those map onto the objects that you're drawing right now? Or
Okay,
that was like a very loose analogy?
Yeah. I know exactly what you're saying. So if we had a surface like a torus, the topological phase is something that lives on the surface. It's like a bunch of electrons interacting with each other in some way on the surface. In an experimental setup, the surface would probably almost certainly be flat. It would be a disk inside, be some crystal interface. But in order to understand, and what you'd be interested in is excitations called anyons running around on the surface. So the actual experimental picture, the surface would be a disk, and it would have lots of little punctures where the topology, where the topological phase is broken. And these are point-like excitations, and these are anyons. So the anyons are nearly points, maybe a few angstroms of region where, and then the braid representation, the Jones polynomial that we talked about earlier, would come in this picture. You could imagine taking one of these anyons and moving it around the others. Or you could imagine moving all of them. In any case, you could think of that in space-time as creating a braid. And then if you do that picture in space-time with time going down, so now the anyons have some crazy world lines, and you have some braid in here. And say they end up in exactly the same place at the bottom as they were on the top. That's useful because then you can identify exactly this Hilbert space, V of this, with this Hilbert space. And the key statement is that this map is unitary. Yeah, I should have said, I did write it, that these are finite dimensional Hilbert spaces. And of cobordism, so I was about to say the key axioms. The first axiom is a surface has a Hilbert space, a finite dimensional Hilbert space associated to it. The second axiom is that if you have a bordism between 2 surfaces, so that's the 3 manifold. Bordisms came up when we were talking about point breaking. You have a 3 manifold between. Then the Atiyah axiom says that the bordism corresponds to a linear map between the Hilbert spaces of the input and the output surface. So this is like sigma prime here. This is sigma. And this linear map, in the case of the braid, is invertible. So it's unitary.
Hmm. So I think
It's
like
very-
you have bosons, fermions, and I guess anyons are things which sort of change by some kind of fractional
yeah.
phase, right? And that's what's going
Well,
on here.
yeah. So yeah. So let me write that word down. Yeah. So you're right. The etymology of this word anion is that fermions have this minus sign when you exchange two identical ones,
Hmm.
and bosons, nothing happens, plus
Hmm.
sign when you exchange. Uh, so like, this would be like photons and these like electrons, for
Hmm.
example.
Hmm.
Anyons, the etymology was any phase is possible. And, an anion, it might be that when you exchange two identical ones, the state vector
Hmm.
goes to e to the 2 pi I over 3, say. I mean, that's an example.
Hmm.
One third
Yeah.
root of unity,
Hmm.
can pop up. But actually, much more beautiful than this is the change to the wave function can be more than a phase. So a phase is just the example of an abelian anion.
Mm.
Non-abelian anions, which are related, for instance, to this 5 halves state I mentioned,
Mm.
have the property that the transition from a state after the braid is not characterized by just a phase, but some unitary transformation, which is a function of the braid you did.
Hmm.
And the theorem, well, slightly. The theorem which is worth writing on this, which was worked with Mike Larson, Zhenghan Wang, and myself. The theorem is that for sufficiently high level Chern-Simons theories, so for example, SU2 level 3, this is not true for level 2, but at level 3 it becomes true. For SU2 level 3, such U's are dense in the unitary group of the Hilbert space. So that means if these are this right kind of anion, like SU2 level 3, what the theorem says, is that you can approximate any unitary transformation from the Hilbert space to itself by a suitable braid.
I see. Is this okay? So I'm not sure what SU2 level 3 is, but I'm guessing this at a high level. This is what's going on. Anions.
Well, it doesn't matter what this is. I mean, these are just names for
right. Yeah, that's what I meant.
Like in Whitten's paper, he says that the Jones polynomial it can be rewritten. It's like an expansion. You can expand the Jones polynomial in terms of evaluations of the sequence of quantum field theory.
But I think basically at a high level, anions are parameterized by representations of the braid group, and this theorem is saying that the image of the braid group under this representation is dense in the unitary group.
That's right.
Okay, great.
Yeah, it's actually dense. Small technicality, it's dense in SU, especially.
Okay.
The determinant.
Sure, I see. So I think what this is basically saying is that thinking of these, how to say, at the end of the day, a quantum computer is supposed to manipulate qubits, and what this is saying is that basically manipulation of qubits are given by unitaries in general, and so you could sort of do arbitrary qubit computation by manipulating these anions. Is that kind of essentially what's going to happen?
Yeah, that's right. But it's it's kind of a slightly different world because for most anion theories, this Hilbert space is not a tensor product of qubits.
Okay.
Like, for instance, SU2 level 3 is essentially the Fibonacci series. So the dimension of these Hilbert spaces grows like the Fibonacci numbers as you add anyons. Dimension 2, 3, 5, 8, 13, like that.
Not a power of 2.
They're not powers of 2. So there's a little awkwardness. It's just a small embarrassment if you did succeed in harnessing Fibonacci anyons and had the technology to braid them and do the correct readouts. In order to take programs in the literature written in qubit basis, you'd have to work in some subspace of the topological space. And that's discussed, that's discussed in our paper. And it's a little bit wasteful. I think we only end up using like 49% of the log of the dimension as we embed these qubits. So there is a little bit of an inefficiency because it doesn't have qubit decomposition. But I think it's actually very nice to realize that quantum computation is not tied to qubits, that there are other models for extensivity.
I see.
And this comes up actually like in Witten's recent work with type 3 factors and so on. It's not necessarily true that the only way something can become extensive is to have disjoint union of systems.
I see. So I guess just being a little philosophical here. So I guess classically with qubits, kind of they're the quantum analog of classical bits, and then your basic quantum gates also are analogs of classical gates because you have and, or, not, etc. That's maybe the most direct analog of classical computation. But you're saying if you take a step back and say, okay, maybe I want some kind of physical process, in this case, moving around anyons, and if that gives me a representation on the Hilbert space, that can be regarded as a kind of quantum computation.
It is, yeah, exactly.
I see. Okay.
Yeah, and as I mentioned at first, I was thinking that maybe this would be more powerful than quantum computing on the qubit level. But it turns out the two are exactly equivalent.
Oh, okay.
They're polynomially equivalent. So it's sort of a vindication of the adjusted Church-Turing thesis, the modern quantum version of it. I think we're back to knowing only only two models, classical and quantum.
Oh, I see. So I guess this must be what you just said must be a theorem, right? I don't know who proved it. So somehow, like any computation, I guess you can do in the anion world, you can do in the typical, the standard quantum computing formulation with the appropriate kind of optimality conditions, right? Like, is that right?
Yeah, that's in this paper.
Oh, I see. Oh, so that's a consequence of what you just wrote, or maybe that's a separate theorem. Right. I don't know. Oh, I see. Great.
No. It's in the same paper.
Oh, I see. What year is this?
Probably around maybe 2002 or something.
Okay. Was this a paper that motivated the creation of station Q in some sense?
Well, yeah, it was some of the evidence. Yeah, it was definitely some of the evidence. I think it was more. I think the actual progress that I took to Craig was more experimental work that was done on the quantum Hall effect. Let me just. Sorry, I kind of interrupted the T axioms. I wanted to.
Yeah. I was going to say that. Let's get back to that. Yeah.
I just wanted to write down the last axiom because it makes it. There's a very nice segue back or connection with four dimensions, which I wanted to show you. So. So let's say, I'm sorry for being a bit messy, but the basic axiom that we have is a surface. You associate the finite dimensional Hilbert space to a Bordism. You associate a linear map between Hilbert spaces. And the last one is there's an inner product. That is, if you have a surface bounding a manifold, three-manifold, so this is my sigma here, it's bounding a three-manifold. This is a special case of a morphism, but the morphism goes to the empty surface. It's empty on this side. So the Hilbert space for the empty surface by convention is just the complex numbers, the one-dimensional Hilbert space. So this means something bounding on the side is a vector. It gives you some vector like dm or psi maybe contained in the Hilbert space of D of
Right.
sigma.
Right. You're thinking of this as a ket vector.
Yeah, that's right.
Yep.
Yeah, maybe I should. And then if it but now suppose it bounds also on the other side, so like M2. Maybe I should think of that as a bra vector. Okay.
Mm-hmm.
So there's a bra vector here. And now the last T axiom is if you glue these together to make this picture, M1 on this side and M2 on this side, then this is, in the quantum field theory, this should be accorded a number, complex number, which is called the partition function, Z. So Z of this glued up thing is simply the inner product of psi M1 and M2, the Whitehead thing.
Mm-hmm.
So that's the final Lakia axiom. And I thought it'd be nice to show you this idea of the universal PQFT, which
okay.
is motivated. The whole reason for thinking about this came from thinking about a subject you grew up in, actually, exotic four manifolds, exotic smooth structures on four manifolds, Donaldson theory. So just remember this picture, the gluing together. Well, maybe I'll leave it in just the way it's above it. So, so there's this beautiful thing called the Kummer surface, which is I'll just denote it K, and it's an algebraic surface inside CP3, and it's equivalent to one representation of it. It's the zeros of the quartic. It's sort of the I equals 1 to 4. So if you just take a non-singular fourth degree polynomial, like summation of zi to the fourth power in each of the four homogeneous coordinates, and think of this as a complex codimension 1 thing sitting in CP3.
Mm-hmm.
That's called the Kummer surface.
Right. So the zero set in C4 minus the origin, then modulo scalars, right?
Right. That's this.
Yep. Exactly. Yep. Mm-hmm.
And there's also something called the logarithmic transform of the Kummer surface, which all we need to know about here is that it's proved by Donaldson theory to be not diffeomorphic to the Kummer surface. So it's a twist of the Kummer surface. You twist some of the elliptic fibers. It's kind of like a four-dimensional generalization of Deng twist. The formula for it has a log, so it's called logarithmic transform. And this is another smooth manifold, but it's not diffeomorphic. It's homeomorphic, but not diffeomorphic to the original Kummer surface. And it's further known that the two differ by what's called an absolute court.
Okay.
So I'll explain what that is. So, it turns out that, let me just draw a generic manifold picture. Here's the Kummer surface. It turns out that there's a contractible manifold, compact contractible manifold C in the Kummer surface. So I draw it as a disk. It's contractible. but it has a homology sphere on the boundary. It's not the real Fortis. And call the complement X. And then it turns out that this logarithmic version, which is different, can be made by the same complement X, but you glue in some different contractible manifold. We'll call it C prime. So they only differ by this contractible piece. So, in fact, the way we know C and C prime are distinct is because using gauge theory, you prove these are distinct. They're different Donaldson or Seibert-Whitman variants. And so you conclude that since they have the same complement, X, they must be different, or when you group them together, you have the same.
I guess it's called the quark, is you take out C and you put in C prime, right? You just plug in a different size
right,
quark,
you plug in a different thing.
Yeah.
But so that means you might now be bold and consider this abstraction, C minus C prime. So this is just a formal object. I want to imagine formal linear combinations of four manifolds that have a fixed boundary. Just allow me to do that for a moment. And now, just like gluing together is some kind of inner product, that was the T axiom. Let's just use that notation. Let's just kind of riff off of that notation. And let's say that X inner product C was the original Kummer surface, and X inner product C prime is the logarithmic transform. And now let's consider this formal thing, this difference, an inner product with itself. So how should we expand this? Just by linear, using bilinearity, we should say this is four terms. It's CC minus C prime minus C prime C.
So this inner product is a number, right? So are K and K log numbers, the partition function of K and K log? Is that what you meant?
Well, there are numbers in a certain ring, but it's going to be the ring of formal manifolds.
Oh, sorry. Maybe I'm confused. There was the partition function inner product, and then there's this other inner product you're writing. Are they the same thing?
No,
Or
but the ring is going to change.
Or is the pairing just gluing?
No, I'm purposely creating this notational ambiguity.
Oh, okay.
It'll resolve in just a second.
Okay.
So right now, I'm using sort of the outrageous notation of taking the inner product to just mean you glue the two things together. I'm like, I'm trying to describe this universal thing. Okay. And a synonym for universal is lazy. You just do what's natural and you don't think. You don't like come up with an actual invariant. So you'd have to think of an invariant to get you to the integers or to get you to the complex numbers. But what I'm saying is we're just going to regard all closed form manifolds as a ring with multiplication being disjoint union. And then the identity is the empty form manifold. And plus will be formal linear combination. Okay. So if you accept that all four manifolds are a ring, then I can take bracket into the ring of four manifolds.
Sorry, is that just Is that multiplication, or what is bracket?
No. It's gluing. So C
sorry.
C is a manifold with a fixed boundary. Everything has a fixed homology sphere boundary. And I glue two together and I get something closed. And if I have formal things and I glue them together, I'll get by bilinearity.
I see. So the pairing is defined only on pairs of manifolds that have their boundaries identified, I guess.
That's right.
Okay.
Yes, exactly.
I see.
That's what's finite. But
I understand what's going on now. Okay. Yeah.
But here's here's a very curious fact. It's just a calculation in topology. The fact is that all four of these terms give the force sphere. You see, these are contractible manifolds.
Oh, I see.
Okay. So when you glue them together, you're certainly going to get some homotopy force sphere. And of course, there might be counterexamples for the smooth Poincare conjecture. We don't know. But in all the things that you can actually make and look at, you can usually figure out that it's standard. And that happens to be the case for these two quarks.
Okay.
So the fact is that each of these is S4.
Yeah, you also meant a plus sign for the last term, by the way. Yeah.
Thank you.
Okay.
Yeah, that would have ruined my punchline. And now they cancel because you have plus, minus, minus, plus. So it's zero in the ring.
Yeah, I see.
So what this little calculation shows you is that this inner product, this kind of crazy inner product into manifolds, has what you might call a light-like vector.
I see. Yeah.
Okay, because you have something inner product to itself is zero, but this thing is not zero, because it behaves differently with respect to x.
Right.
But this can actually be used as the core of an observation that Donaldson theory cannot be expressed as a unitary QQFT. In Whitten's work on Donaldson theory, the year before he wrote his paper on Jones polynomial, he wrote a paper on Donaldson theory, putting it into the context of TQFT. And in fact, it's actually in that 1988 paper that Whitten introduced the phrase topological quantum field theory. But that paper involves what he calls the topological twist, which breaks unitarity. So Whitten had already moved away from unitarity in order to construct gluing axioms for Donaldson theory.
What does unitarity mean in this context? The
point is, the point is that
is it that you need a positive definite inner product?
Yes, exactly.
Okay.
Yeah, unitarity with respect. I know some people talk about like UPQ, right, where they're P positive and negative directions, but I'm not thinking that way. I'm thinking more the physics way, where unitarity means you preserve a Hilbert space inner product, where the Hilbert space inner product is a positive definite. Okay. So symmetries, the unitary group in the language I'm using now is the symmetries of a Hilbert space, and a Hilbert space in the definition I'm using now has a positive inner product.
Are you jumping ahead? Are you saying that if you try to apply these Atiyah axioms to the four-dimensional case, you're going to run into problems? If you want your vector spaces to be Hilbert spaces.
Exactly.
Okay.
If everything's a Hilbert space, and the pairings are Hilbert spaces, and you expect the inner products to be unitary, to preserve to be compatible with the positivity, then this formalism, you see now we see why I was intentionally creating an ambiguity with the notation, because we could just use another color of ink and slip in a functor here. We could talk about V of this difference, right? And V of this difference. And then this would become the part, then this would become, maybe for the subscript Z here, this becomes a partition function in the usual sense, because it would be the inner product of two. See, these were manifolds to begin with, they're formal manifolds, and we inner producted them by gluing them together in a formal way. But we could apply the functor and say, these are now elements in a finite dimensional vector space with a positive definite inner product. And then when we take this, we're taking its norm squared, which is a positive number. It's not zero. But by this calculation, it would have to be zero.
I guess. How do I say?
So what I'm saying is that the
Yeah.
distinction, the mathematics which distinguishes the Kummer surface from its logarithmic transform cannot possibly be captured within a unitary 3+1 dimensional
Yeah.
TQFT.
I see. I guess also because this is a topological. Actually, I'm a little confused now because if we're, as you said, k log and k are equivalent topologically, but not smoothly. So
Yeah, so you should just think of it as plain different. The topological category has no relevance here.
Oh, I see. So you're sorry. It's called the topological quantum field theory, but the underlying object
Yeah.
is smooth manifolds.
That's just a tragedy in the language where we can't do anything about it.
I see.
It should be called the smooth quantum field theory.
I see. Okay. So then the only other question I have about what you just said is that you need your functor to be, I guess, norm preserving or respecting in some sense.
No, but it has to be true because the fact is that smoothly each of these inner products is the four sphere. Inner products in the previous sense that each of these brilliants is the fourth sphere. So if we get to the numbers, to the complex numbers by applying some functor, so we apply some functor which turns manifolds into vectors and manifolds with boundary into vectors and turns closed manifolds into numbers. Then if the manifold turned out to be 0 copies of the four sphere, it has to go to this number 0.
I see. I think the functor automatically preserves the appropriate structures. That's right. Yeah,
the functor, kind of by definition, the functor on diffeomorphic things takes the same value.
Yeah, okay. So the main result you wanted to present is that this positivity can be restored in 3 dimensions or is true in 3 dimensions.
Yeah, that's right. So this is just like an observation that the Witten's work was sensible.
Okay.
He needed to move away from unitarity. But the fact that I wanted to mention is that if you lower the dimension by 1, if you play this whole game, right? So you take any surface.
Although in dimension 3, smooth and topological are identical, right?
That's right. So we will define a vector space over a surface to mean this will be like formal linear combinations of 3 manifolds such that the boundary of the 3 manifold is the surface. Okay? And then we have a map. It's like a bilinear, actually technically sesquilinear pairing from 2 copies of this to the vector space over the empty set. So the empty set means closed. So it's exactly the same picture we had before, that here's the surface, and it bounds a 3 manifold on the left, that's like the bra, and it bounds a 3 manifold on the right. You glue them together and you get something closed. So that's the vector space of linear combinations of 3 manifolds that bound the empty surface. And the theorem is, this is a theorem with Kevin Walker and Danny Caligari. It's also a 7-year project. The theorem is that this has no white-like vectors.
So it's just positive definite then, right?
Yes, it's positive definite. You just say it automatically positive definite if this target thing was the complex numbers or the real numbers. But this target thing is this crazy ring of all closed 3 manifolds.
I see what you're saying. Okay. I was wondering why you emphasize no light vectors. Okay, it has
Yeah.
no.
So I mean, the
Yeah.
formula for this is if you have summation AI MI
Mm-hmm.
cross summation
Mm-hmm.
BJ MJ would go in this pairing to summation AI BJ bar MI e to MJ, something like that.
Mm-hmm.
And basically this says no non-zero combination in this space pairs with itself to give you zero. You never get a cancellation like we had here in 4 dimensions.
Yeah. Okay.
Uh, and I've wondered, I mean, this is something, maybe for your listeners to think about. I've wondered if this is an important transition, basically this is happening. I mean, a lot of stuff changes, right? As you go from 3 to 4 to 5 dimensions. And it's interesting to wonder, like, what's fundamental and important, and, why is the macroscopic dimensions of the universe the way they are and all this. And I've sometimes wondered whether this could be, brought into a theory of everything.
Okay.
Because all the higher dimensions have light vectors, and then 3 and below they don't.
I see. Okay. Okay. This is very fascinating. How does this relate to topological quantum computing, or is there a segue?
Well, I'd say rather this is the segue from four manifolds, thinking about four manifolds and their smooth structures, to TQFT. And here you're thinking about TQFT mostly on closed surfaces and closed manifolds. And then as you get kind of more and more industrial in your thinking, you realize you're not going to be able to build topological phases, on curved manifolds. They're going to be like samples in a Dewar and a cryostat. And then you start thinking not about these curved surfaces, but you think about like the little disks that'll have anyons in them, and then you start braiding them. So I'd say that's the direction. This last discussion was sort of pulling back toward my home as a manifold topology.
I see. Okay, we did a bit of a U-turn, but that's fine. Okay. Let's see. Is there anything else you want to say about topological quantum computing, or should we get to some recent thoughts of yours in terms of economics and quadratic funding?
Yeah, I think I think we should move on. I mean, maybe the last thing that I'd like to say is about the topological quantum computing is that it's sort of at this moment hung up in many ways on materials science issues, actually producing engineering phases of matter that have the right kind of anyons and the right stability properties. But something that I think is quite interesting is there's a recent Google paper where they used their transmon qubits, the very standard superconducting qubits, to engineer non-abelian anyons in their system. So it's like a debate, perhaps, whether they simulated or made the anyons. But I think there's no distinction between. I don't think that's a real issue. I think you can just say that they can create non-abelian anyons within their platform. So the point is that the idea of using braiding and topological ideas to do computation does not necessarily require overcoming these material science issues. You could instead simulate anyons in a more conventional qubit architecture, and then do your computation by braiding them and achieve protection against error in the same way you would have in a condensed matter system by keeping the anyons far apart.
That theorem that you cited a while back was some kind of equivalence between the anyon paradigm of quantum computation and sort of the standard qubit style. are you saying that based on that equivalence, there must be some way of representing anion computations in qubit computations, and if you sort of follow that faithfully, you can sort of get away with not having to have
that's
an innovation
right.
in material science? Yeah.
That is right. You
Mm-hmm.
can, the fact that there is that equivalence means there is a path.
Mm-hmm.
But I think the authors of this recent Nature paper, without perhaps even knowing that equivalence, just found a very nice natural mapping to produce Ising anions in a Google chip. So so that means that it breathes new life into the idea of computing vibrating anions without necessarily overcoming the material science issues that were like holding up progress on the quantum Hall effect.
I see. Okay.
So I think it's going to turn out to be a competitive way to protect quantum information, competitive with like all the best codes, for example.
Okay.
The more conventional thinking, is to wrap qubits into these large codes and have logical qubits and protect information that way. But an alternative is to use whatever your underlying architecture is, use it to manifest anions, and then rely on separation of the anions for the accuracy of that computation.
Okay. Anyways, this is going to go outside my knowledge here, so maybe we should stop here and then move to the economic stuff if that's.
That'd be fun. Let's talk about that.
Okay, great. Okay. So let's see maybe just to segue. How did this more recent aspect of your set of interests come up?
Well, I've always had some interest in like the world's problems.
Unusual as a mathematician, I must say.
What's that?
Unusual as a mathematician, I must say.
I mean, in the early 80s, I was invited to join this group of physicists that, even though I wasn't a physicist, they consulted for the government called Jasons on problems that they were the government would bring them. The reason I was invited is I gave a lecture on my university campus on arms control, and after my talk, one of the physicists, Henry Barbanel, came up to me and said, "Well, that was an interesting lecture. Why don't you spend the summer with us at General Atomics, and then if you give this talk again, you'll know what you're talking about." So it was kind of a backhanded compliment, but I took the bait, and I was interested in trying to like game theory, what it had to say about the standoff we had at the time with the Soviet Union. Whether there are any ways to make the world a little safer around the edges with different protocols. And of course, one of the things I realized is that there's a huge gulf between theoretical ideas and practical implementation. And in the sort of social economics that I've gotten interested in recently, that also rears its head quite a bit. There's a whole academic subject of voting theories, but very sophisticated ideas. And I'll mention one called quadratic voting. But when you look at like the way the world is, even the most basic stuff, someone just stands up and shouts, "It's all a hoax! It's all a hoax!" So all the theoretical niceties seem perhaps irrelevant if you can't even control what the fact set is. But laying all that aside, the segue to the real world, there's an idea that was introduced by Roger Penrose's father, Lionel Penrose, in 1946. So the UN had just been founded at the end of World War II, and he was thinking about how the General Assembly should be representing countries. And, like in the US, you have the House of Representatives, which is roughly proportional to population, and the Senate, which isn't, it's 2 per state. Well, Lionel Penrose gave an argument in this paper he published in 46, saying that the correct answer was the square proportion of the square root of the population. Well, let me explain what his reasoning was. By example, so suppose you looked at Denmark in 1946. So Denmark had a population of 4 million people approximately. And India had population then of 400 million people. And in the model that Penrose had in his mind, he said, well, everything in life follows this bell curve. And that as you increase the number of samples, the variance goes linearly, but the standard deviation obeys the square root law. So this basic square root law of, it's the same law if your random walker is moving unbiased on the line. After n steps, his expected absolute distance from the origin is about square root of n. The same square root law says that because India has 100 times the population of Denmark, if everyone in India were voting on a close issue, their chance as an individual that their vote would tip the entire country's decision is 1/10 what a Dane would be able to do.
Okay.
So that the influence of an individual Indian within his country in terms of tipping the vote, whether it's yes or no, by square root of 100 being 10, he has 1/10 of the influence. So in terms of the representation, to compensate for this, he needs 10 times as many, India needs 10 times as many representatives. So the idea is, in Penrose's model, he wants every person in the world to have the same influence at the United Nations. And he's assuming that countries vote each country votes in a coherent way. It expresses its vote in an undivided way. Then if your influence within your country is 1/10 of the Danes, then your country should have 10 times as many votes in the UN so that the individual influence is 1/10 times 10 equals 1.
Okay. I'm still trying to think about this in the back of my mind. I mean, so if you add independent variables together, IID variables, then their variance scales linearly, and therefore their standard deviation has the square root property. I'm trying to map what this IID assumption is to the voting situation, and I guess all voters make up their own mind.
I think in this model you have to think that you have to make a zillion improbable assumptions.
Okay.
Everyone votes. Everyone knows what the issue is. The votes are all counted correctly. But the idea is that in a close issue, we should think that the decision is being pushed by fluctuations around the mean being 0 between yes and no, and that the size of these fluctuations obeys the square root law. So, every voter saying yes is moving to the right, and every voter saying no is moving to the left. So the decision is a random walk, and the decision is just whether the output is positive or negative. Yes, no. So the chance that an individual vote tips the balance in this random walk is proportional to the square root. Okay. So he introduced this idea of square root representation. In general, in this voting theory, there's a phrase that's used, digressive proportionality. I mean, it's just the idea in situations of unequal power, unequal populations, when things are unequal, you just ignore that and give each individual or each group an equal voice, or do you try to in some way choose a weighting which does a better job of optimizing some overall utility function. So it's possible to reverse engineer and construct some utility function for which this square law, is the optimum. And but you could imagine other laws. You could imagine taking other powers. In fact, there's a book which I read after learning about Penrose's paper called Radical Markets. Written by Glen Weyl and Eric Posner. And this radical markets is kind of a play on words because it means both innovative, but it also means square root. And one of the things remarkable is this idea of squares and square roots, or more general weighting schemes, appears all across social economics. So there's radical finance or quadratic finance. There's there's Glen Weyl founded a company to explore an idea of his called radical polling. And I thought this was a very interesting idea. So if you look at results of opinion polls, they're almost always bimodal. If you take any controversial subject like, abortion or participation in a war or taxes or free speech, or you present people with almost any polling question, you tend to get very strong yes and very strong no answers. And very few people are in the middle. And you might think, well, this is bizarre because why isn't it Gaussian like everything else? Why don't people say, well, there are like 10 factors that contribute to my decision at some point, some way, and some point the other, and therefore, I'm more in the middle. And the explanation that was given is if people decide to take 10 minutes out of their day to speak to a pollster, then they really want their voice heard, so they amplify their biases or their point of view. And the idea that Weyl had is instead of letting a person register an opinion on every question, on a scale of, let's say, 1 to 5, they're given a spreadsheet and they only have a certain number of tokens to use to record their opinions. And recording an opinion in the middle may use just one token, but more radical opinions would require a progression of tokens, more and more tokens to express more radical thoughts. And then the interesting thing is apparently not just the result of the poll, but since they're doing it on a computer, you can watch them run out of tokens and panic and then change their answers to move to the middle in earlier questions to save some tokens for what they care about. So, but then sure enough, if you make more extreme positions more costly, then people choose to express intermediate positions. One of the things that I thought was interesting about this is when I have an idea, the most I would do with it, if anything, is I would write a paper on it. But when Glenn gets an idea, then he would create a company to see if it works in practice. So he actually had a company that tried to sell this polling to maybe the few politicians that actually care what people think.
So does this go by a name, this result?
Well, I think it's called I think it's also called quadratic polling as opposed to quadratic voting. What's quadratic about it? It's basically this escalation of costs.
Okay.
But let me delve actually into quadratic. The thing I wrote about was quadratic finance. So this is a way of allocating funds for public goods.
Mm-hmm.
So let me just tell you the formula for quadratic finance. I put the name on the board. So the idea is that you have the index I will be citizens.
This also goes by the name of quadratic funding, correct?
Yeah. Maybe, is it only under that name? Maybe. I think I've heard both.
Okay.
But let's.
Okay.
So the basic formula is that if and CI will be the contribution to some good, like a public park or clean water or something like this. This is like cash contribution.
Right. You're trying to figure out how much individuals should contribute to some public good.
Right. And then the formula for what to spend, so the budget item, the budget amount, will be noted by phi, and it's this formula. It's the square of the sum of the square roots of the individual contributions. So let's just compare this with the simpler model, which is just charitable giving.
Sorry, so this phi is saying what? If each citizen contributes CI, then phi says what?
Yeah, well, that's how much the government would spend on this project.
Uh-huh.
But a simpler formula, which I'll write as phi charitable, would just be summation of CI.
Mm-hmm. One-to-one matching, right?
Well, yeah. So in other words, every person decides what they want to contribute to, a new park in their neighborhood,
mm-hmm.
And then you sum it up, and that's how much there is. So there's no coercion. People make their contributions, and if there's enough, the project gets done. Now, of course, a formula like this can easily lead to a decision to spend more than anyone has decided to contribute. So this is itself, you might call it more of a polling mechanism than a funding mechanism. Your willingness to lay out this amount might dictate a larger amount, and then that difference has to be covered by taxes or something else. And then there could be a feedback. Then you're informed your taxes go up for this, then there's some question whether you get to change your original contribution or not.
Okay. Okay. So you wrote these two formulas. Let's see. How say there isn't a question or problem that we're trying to solve yet. Maybe it would be good to explain.
Well, no. All this is in the economics literature. This is all set up in terms of some optimization problem. Like you make some assumption that everyone has a valuation function, and it's like at least smooth and perhaps monotone. There are various assumptions you can make, and then you want to show that some mechanism based on all these assumptions ideally is a maximum. It maximizes total utility. So there should be some total social utility that could be maximized by some method. And quadratic funding or finance fits into this context. You can, set up a mathematical model in which it's the solution. But what I think is the thing that actually got me interesting is a connection to Kant's categorical imperative that was the quadratic funding, which was pointed out in this paper by Weyl, Buterin, Vitalik Buterin.
Right, of Ethereum fame, right?
Yeah, that's right. And Hitzig. So they had a paper around 2020 in which they claimed that this formula could be derived from Kant's categorical imperative. So roughly what Kant was saying is that you shouldn't be selfish. You should make your decisions based on principles where you'd be perfectly happy to see those principles become universal principles that everyone follows. So they wrote down a differential equation, which I'll write here. So they said, well, let's look at homogeneous formulas like this, but not be committed to the inner or outer functions. And we already saw that you could just have the identity as the inner and outer functions, and you get some model that's like charitable funding, or you can have this proposed quadratic finance that has a square root and a square. It would be weird to have a square root and a cube out here. That really wouldn't work, because then the answer wouldn't be gauge invariant under change in currency. If you double the value of a dollar or something would change. So, but there is a question, what kind of functions could you get? So they consider writing the outer equation like this, g of the summation by some inner function. And then they write down the derivative of this, partial derivative of this with respect to one citizen's contribution. It's equal the summation
Yeah, okay, so, please explain this.
Yeah. So I want to explain this. So, so this really should just be proportional. One way of understanding this is this side being constant. They consider some version of the categorical imperative. It's saying that the contribution, you see, the function h is sort of, this is sort of the equalizer function. The square root in this example is designed to somehow appropriately compensate for the fact that all players are not equal. That people who have less means perhaps should have a smaller say in how funds are spent, but they shouldn't have no say. And it shouldn't be as small as proportional to their wealth. There should be, this is this digressive proportionality. There should be some way of assessing, and this internal function H is supposed to represent the way the community sees the contribution.
Yeah, I'm still trying to unpack the categorical to translate the philosophical principle of the categorical imperative into a mathematical.
Right. And I'm not sure. It's and I sympathize with you because it's not the translation is not straightforward in my mind, but I do feel it's there. So the point is that the categorical imperative is essentially saying that you should make your decisions in a way that these motivations are the motivations you use to make your decisions should be motivations that the rest of the community can also adopt.
Right.
So if this is your weighted contribution, it says if you decide that to increase your funding by 1%, the other people in the community have access to that same information, and they should also decide to increase their contributions by 1%. So this side should stay constant.
So it sounds like basically you need to have a homogeneous function, but if you, for example, squared the right-hand side, you'd still have that property, right? So like I think what you just said was, okay, if everyone increased by 1%, so if every h got replaced by 1.01 h, then the numerator and denominator would cancel. That's true. But if you also squared the entire expression on the right-hand side, that would still be true, right? So that's not enough to pinpoint the form.
Yeah, let's hold that reservation.
Sure. Yeah. Okay, we can move on. Okay, but it has at least that property. Yeah.
And this side, this side should be constant. Is just basically gauge invariance of currency.
Yeah. When you say constant with respect to what exactly?
Well, constant with respect to changed circumstances. That is, like here I was arguing, if new information inspired one party to increase their contribution, then it should inspire everyone to increase their contribution, and therefore this side should stay constant. Here, if for instance, if the currency, was changed, if you were measuring in pennies instead of dollars, then the total amount that is spent, which is this outer function, should grow proportionally to the contribution as you change the basis of the currency.
Okay.
So, by the way, something interesting in this claim, and I'm with you on all kinds of reservations about it, but Bertrand Russell he wrote this really lovely book, The History of Western Philosophy. And one of the points he makes in it near the end is that almost all philosophers work in syllogisms, but he says that what we know, is that the laws of physics are not handed down as syllogisms; they're handed down as differential equations. That's what we've learned in the last 500 years, and Well, he made that remark just to castigate his fellows who were less erudite than him, who didn't know as much math. He said, we won't really get to the bottom of things by modus ponens. You have to try to formulate things in terms of differential equations. And this is the sort of first glimmer that I've seen of philosophers. I mean, they're trained as economists, but they're really entering this domain of philosophy now, trying to move toward differential equations in order to figure out what's right to do. Growing up in my household and then my adult life, talking to my father, he was very much interested in Spinoza. Actually, Spinoza and Gödel. He was a logician and a philosopher. And he would try to get me interested in this mammoth book of Spinoza's, his Ethics, where Spinoza tries to figure out how to act in the world based on some axioms and make all the deductions. And I could never take one step after another. Like 2 lines of deduction and I'd already be lost because everything was swimming around in my head. I didn't know exactly what the words meant. I didn't know what a higher principle was or what a base consideration or and part of the problem was probably it was translated from Latin into English, but probably even if I knew Latin, it wouldn't have helped. It just seemed like the language is too slippery and doesn't survive deduction. So, when I saw this, it was kind of the first glimpse that I could understand of success in trying to apply mathematical thinking to philosophy and ethics. Even though we've been trying to do this as a race, for almost 3,000 years, or 2,500 years, Parnassus and early Greek philosophers were always trying to make these deductive steps. But because they were working in syllogisms rather than differential equations, maybe we've been stymied. So this is what I found exciting about this. And let me just write down the next line that they deduced from this. So
okay.
They just say, this is basically G prime. This is just chain rule of the summation. And this internal derivative, since this is only one of the citizens, Cj, it's just times H prime of Cj. And this should be proportional, again, to this right-hand side, which I'll just write as summation H Cj. And then what they say is that the two factors on the right and left side break up into collective, which is the sum, and individual. So they use the ansatz that the equation should be solved by solving them each separately. So they say, if you want these to be proportional, you can just turn this proportionality into an equation and turn this proportionality involving the sum into an equation. So the outer equation says the derivative of something is proportional to the something. So that means g of x should be proportional to x squared. And the red circle says that something's derivative should be the inverse of the thing. And that's solved by h of x being proportional to x to the half plus some other constant. And then you can figure out, based on boundary conditions, that these constants should vanish, just simple arguments like if no one wants to spend any money, no money should be spent, things like that. You can figure out what the constants are and that the proportionalities, the coefficients should both be 1. Those are not hard to fill in. But this is what I wanted to show you. This is the thing that sort of inspired me to think about these models is seeing this deduction of this formula, the outer square and the inner square root, from a differential equation, which can arguably be linked to the categorical imperative. Though I agree with you, that's a somewhat subtle point if that works or not.
Yeah, I mean, there's some extra reasoning steps that I guess we won't work out here, but yeah, there'll be references that one can follow. Yeah, there's more thought into that, translating that categorical imperative to a mathematical expression.
Well, I think it's just not thought that we don't have time to work out right now in discussion, but I think it's not really worked out. I think it's an inspiration more than a theorem.
Sure.
And it's a direction. I think it's a very bold direction. It's like challenging the mathematically inclined to reason using all their tools, and not just syllogistically about philosophical, political, economic issues.
I see. So interesting. Okay, so just to recap. Excitement. I don't know if you had what more you had to say, but to
no, I didn't have. I'd have no more to say.
Okay, but to summarize, it sounds like you had a few influences into how you got interested in this. First was, I guess you said your father or various intellectual predecessors like Lionel Penrose got you thinking about these things, and then I guess maybe your innate interest in social issues. But then also this sort of paper by Weyl and others sort of translating philosophy to equations. And I guess the bigger picture is that, and also Bertrand's criticism of philosophy of not using equations. All that mixed together is kind of what got you onto this path. Is that right?
Yeah, I found the Lionel Penrose paper after I'd embarked on the path. It was really my father who. It's funny because I had a hiatus of about almost 60 years where I didn't think about this stuff. But as a youth, my father tried to lead me through Spinoza, and I was frustrated and felt incapable of understanding what he was talking about. And that was at the beginning of my life. And now, late in my life, I see like a slightly different approach, which is more analytical. And I find it inspiring that people haven't given up, just because people have been thinking about these questions of how to deduce what's right, for thousands of years. Just because we haven't cracked the nut yet, doesn't mean we can't.
That's interesting that how do I say, very crudely speaking, there are going to be two camps in this regard, right? Just to be extreme, back to your bimodal analogy. There are the people who are going to say, I think most scientists are in this camp, which is that kind of morality and science are completely different domains, right? They don't impinge on each other. What is versus ought distinction, and so kind of maybe this is a hopeless task. And then you have people that are maybe more on the EA spectrum that are like, okay, let's try to optimize how we let's say spend our money to maximize social good, and what you presented here is more on that latter spectrum. It looks like, and even more specifically, the claim that maybe the right way to do it is through differential equations rather than through formal logic. Can you respond to that?
Yeah, actually, let me respond with slightly outrageous thought. I've often thought that formal logic might have an alternative foundation. There might be an alternative choice, which is more like a path integral, which is closer to analysis in differential equations. Because if we reason outside of mathematics, we usually reason based on preponderance of evidence, and many threads of reasoning, none of which are precise, come together and create a feeling about something, and we go with it. which feels a little bit like a Lagrangian formulation. There's an action along each path, and we're adding them up.
Sure.
But mathematics doesn't exploit that. One mistake means the argument's wrong.
Or actually, maybe what you're referring to would be more kind of what people would think of as Bayesian reasoning.
Oh, I see where each thing. Well, that's perhaps. So each step has a probability associated to it.
That's right. You have a space of hypotheses, and you assign a prior.
Yeah.
I don't know if you've thought about that, but I think that's where this would go.
Is there a quantum version? I'd be more interested if there was an interference.
Oh, a quantum version of that? I don't know. I wouldn't be surprised if there is one. I feel like quantum is something you could prepend to anything these days, but maybe there is.
That would be exciting.
Okay, but I do like this idea of differential equations. This thing that Bertrand Russell said. I'll have to think about it more, but I've never thought I would see a differential equation in a. I mean, first of all, I don't typically see math and morality mixing. But if they were, I would think it is more of the sort of on the deductive route. But now bringing in differential equations is quite unexpected, I must say.
Yeah, so I'm only about where you are on this. I'm just trying to get my head around whether it's useful and how it works.
Okay, great. Is there? I don't know. Actually, is there? I don't know. Are you a lone wolf thinking about this, or is there like a group of people, or a body of literature, or a community that houses this?
Yeah, I'm a bit of a lone wolf. I have a contact with Glen and some of his friends occasionally, but I'm thinking quietly.
Okay, all right. Maybe just to let's see to summarize. I mean, you've I don't know. You've had such a long and diverse career. I don't know. Maybe we could end on any advice that you might have to listeners in terms of what they should work on, how they should prioritize maybe different interests. I don't know. Like what career advice might you give to someone?
It's funny. I think the advice I'd give harkens back to our discussion before you hit the record button, which is life is pretty unpredictable, and that it's probably better not to have a too well thought out game plan and adapt as you move. I mean, it sounded like your history, which is fascinating to me, is an example of that. Doing the kind of math and doing the kind of physics that inspired you. And, then when the moment came when it didn't look like it was going to lead to exactly the right next job, you thought, oh, well, I have a lot of things I can do. What's the most interesting one? And I think that's a good way to move and think.
Great. All right. Well, thank you so much for your time, Mike. This has been a lot of fun.
Yeah, me too. Thank you.